Okay, so we're going to keep our definitions up here somewhere in the corner so that we remember what they are. Maybe make them a bit smaller. And yeah, now let's kind of explore the validation algorithm. So if you watched my CSE series, you will know how to verify a program with respect to a whole logic triple. So can we do something very similar for Lisbon logic? So let's have a look. So I'm going to draw this program. Now, an oval, this is going to represent a set of states. Now, if you remember, we had in compositional symbolic execution, we had symbolic states, hat sigma, and they represent. I'm not sure how to do a representation. Maybe like just do like an equality for now, but they represent a set of states. So some sigma such that some property of sigma holds, right? And this, in fact, this P here is, well, we can take that as the precondition of our program, right? So this initial state is just our initial program. Now, as execution progresses, I'm going to make this smaller so we can fit it all on. As execution progresses, we're going to be transforming our symbolic state here. So this is, you could say, this is some command, it does some transformation f. If we start with some sigma, we're now gonna have a different sigma, and it's actually just gonna apply f to every concrete state, right? You can imagine that this new sigma is this transformation f here. Now that's a simple transformation. That's a mapping, right? Every input state has some kind of output state. What we can also have in our program is branching. Now, how does branching work in in symbolic execution in general? Well, we basically split our symbolic state into two parts. So if we have an if statement, if some expression E, then C1, C2. If we have an if statement, then our state is going to be split into like the partition that satisfies E. So the partition where E is true, and the partition where E is false. So let's visualize that here. So we are actually going to split this like this, and we're going to have our two partitions. Okay, so we split our state into two partitions, and that's on a conditional branch. So our command is now this. Have one partition going to this side, and another one going to this side. Okay, so that's another thing that can happen to our program. What else can happen to our program? Well, our program can terminate, okay? And I'm just going to represent this as this arrow going downwards. Like, let's say the bottom of the screen here is a terminated program. If it didn't terminate, then I could just draw like this loop. What else could happen with our program? Well, we mentioned non-determinism in the last part. So what does that mean? Well, our partition of states is the same, but we end up with two different paths, essentially. So instead of narrowing things down, we end up with a state that is a symbolic state that is the same size essentially. It covers the same initial states. We did not do any kind of filtering, right? Because you can imagine if I were to write down the states here, then now it's going to be right. So in the left path, E is true, and the right path, E is false. But here, well, we have some condition. Let's call it E2, and E2 does not depend on the input state. Okay. So I'm going to write this down. E2 not depend on sigma. And that's important. If it doesn't depend on it, well, whoops. If we do this one here, then it's actually just going to be exactly the same, right? Because it's not a transformation of the initial state. So that's why we're keeping the same shape here. Now you can imagine, this program here terminates, and this one here it branches again. So yeah, so you can imagine again we have some regular deterministic branching that does depend on this input state, where the input state is whatever this thing is, and then these will eventually terminate. Now, what we did in whole logic validation is we basically said, okay, so, every trace that terminates, we're just going to check, does it satisfy our post condition here, right? So we're just going to ask the question, does it satisfy Q? And we're going to do this for every single trace. Okay, and that is Hoare logic, or Hoare triple validation. That's what we're doing right here. We're checking every single one. So essentially we can follow a single trace and check whether it satisfies Q. Then backtrack, follow another trace, check does it satisfy Q. And so on for every single trace we can take. And of course, if there is some trace that doesn't terminate, which we will again denote with this kind of awkward loop. If there is some trace that doesn't terminate, well, we just ignore it, it's fine. What does it mean instead to do? Oops, I deleted too much. What does it mean instead to do Lisbon triple validation? Well, in particular, when we have this non-deterministic branching, we only really need to follow one of these, right? The existence of just one terminating path is sufficient. So let's pick them. Let's say we have these traces, we've collected them up. We get this one, right? First we get this one. It covers half of our initial state. So, it also satisfies the post condition. So we're like, okay, we've covered this part of the state. So we can mark that. Okay, we've covered this one. Now we get this one. This covers the other half, right? But let's assume that it doesn't satisfy Q. Okay, so we can't pick this one because it doesn't satisfy it. And let's also say that these two do end up satisfying Q. And so we can mark them. Whoops, the errors get really messed up when I do that. Not sure what's going on. Yeah, so basically we've reconstructed our entire initial state from these three symbolic states, right? If we okay, you can see that the shape matches up. If we were to put them together, we get back the initial state. Now, how do we decide this? How do we decide that? How do we determine that we've covered the entire initial state? It might be a bit hard, right? You can imagine. I won't go into the specifics, but it's hard to determine whether we've covered the entire initial state, right? Because that's what we're quantifying over. We're quantifying over the entire initial state that satisfies P. So what if we do this in a more modular fashion? So at each step, right? At each step, we are going to check. At each branching point, let's say, we are going to check whether we have covered the entire input state. So let's look at all the branching points. Let's look at this one. Okay, let's look at the shape of this. Well, to reconstruct this shape, we need both of these blocks. Okay, that's there. So now the input state is this. This is kind of a divide and conquer algorithm. The input state is this. And to cover it, we need both these parts. Okay, let's recurse back up. Now we have this state here. Well, to cover the entire one, we can either pick this one or we can pick this one because both of them have the same shape. Which one do we pick? Well, ideally we pick the one that that satisfies the post condition. So we're going to pick this one. Okay, so let's mark that. Now we go further up again. We recurse up, and we see again we need both parts. There's not much choice to be made here. And again here there's no branching, so you can just select the entire thing. And at the end, we basically end up with this path. And in fact, if we take the leaf nodes, then it's sufficient that we analyze the satisfiability of the post condition for the leaf nodes. And we have covered the entire initial state just by construction, just by this simple recursive algorithm. And this is the essence of the collecting semantics in my algorithm, of keeping track which states we want to check for satisfiability of the post condition. Now you can also imagine that there is, let's say this one doesn't terminate, right? Let's go back to that example. Yeah, let's say this is an infinite loop. Then if you remember what I said, traces with infinite loops do not have derivations. So in fact, we can't even pick this path here. This path, because it loops forever, is non-existent to the algorithm. So the only thing we can do is check whether this state here covers the entirety of the initial state. And there is a decision procedure for that, which I've come up with, and I think I will cover it in another video. But yeah, essentially we can do this modularly at each step.